Hi there! Today we're going to talk about spectroscopy. Spectroscopy is the study of the interactions between matter and radiant energy, or in our case, light. Let's move outside to learn a little more about why scientists use spectroscopy. Light is one of the only tools that planetary scientists have to study distant objects. Take a look at that planet up there. What if we wanted to know what elements were contained in its atmosphere? It would be an awful lot of work to travel there. So planetary science use spectroscopy, of course! Let's head back into the classroom to see how it works. First, we must review the structure of an atom. We must get very small. Here is a model of the lithium atom. It contains 3 positively charged protons in the nucleus and 3 negatively charged electrons around the nucleus. You may notice that the electrons are positioned in 2 different energy levels. This is important. With 3 positive charges in the nucleus and 3 negative charges around the outside, the energy levels must be positioned a certain distance from each other so that the atom doesn't collapse in on itself. Let's look at another element like beryllium. We now have 4 positives in the nucleus and 4 negatives surrounding it. In order to keep this large attractive force from collapsing the atom, the energy levels must set up farther apart from the nucleus. Each element has a unique distance between energy levels. We're back looking at the lithium atom now. An electron can jump from one energy level to another if it absorbs some energy. So where can this energy come from? Light. Light is made up of packets of energy called photons. Different frequencies or colors of light carry different amounts of energy, blue being high and red being low. When these photons come in contact with an electron in an atom, the electrons absorb their energy. But there is a catch. An electron will only absorb the photon if it carries enough energy to land them exactly on the next energy level. Spectroscopy is powerful because every color of light has a unique amount of energy and every element has a unique distance that the electrons like to jump. Back to the lithium atom. Let's say that a photon of red light flies toward this lithium atom. The electron notices the amount of energy the red light has and absorbs the photon, jumping out to the next energy level. It then emits the red light back out as it falls back down to its original location. Now what about blue light? A little bit more electricity. The electron ignores the blue light because it carries too much energy and would jump the electron past the outer energy level. What about the beryllium atom? First, the red light. The electron notices that the red light's energy will make it fall short of its next energy level and therefore ignores the red light. But what about blue light? Blue light carries just enough energy for the electron to jump energy levels and therefore it absorbs it. The electron then emits the same blue photon and drops back down. Oi! All that talk about tiny stuff makes my head hurt. But we figured it out! Spectroscopy takes advantage of the unique properties of light and the unique structures of atoms. Now, we'll take a look at some real examples. Let me pick up this glass tube filled with a gas and shine a light at it. Could someone get the lights, please? Thanks. First, use your diffraction glasses to look at the floor. Look, the colors of the rainbow. Except two of the colors are missing. Yellow and blue. Now let's use our diffraction glasses to look closely at the glass tube filled with gas. The only colors you can see are yellow and blue. The electrons in the gas must have absorbed the yellow and blue light and then emitted it towards our eyes. You can look up what element has energy levels that would only absorb yellow and blue light to determine what is in the glass tube. Lights, please. Thanks for listening. I hope you all learned something about spectroscopy. See you tomorrow.